Ladies and gentlemen, welcome to our foray into the world of Apache Airflow. Today, we're going to demonstrate how to orchestrate audio, video, and other media processing tasks using this powerful tool. Are you ready? Let's dive in. We'll guide you through a media file analysis example using ffmpeg and turnkey cloud services like Cloud Speech to Text. The best part? It's all built on an open source foundation with Apache Airflow code. Specifically, we'll be leveraging operators for speech to text, custom Kubernetes pods, and even operators for cloud storage. In the end, we'll have a seamless end-to-end media analysis workflow that's fully managed, serverless, and can be executed on demand or on a schedule. Now that we've established the vision, let's dive headfirst into the Google Cloud Console to set up these resources. The first thing on our to-do list is to enable the API, especially if we're using a new project or one that hasn't yet used Cloud Composer. Now, let's create an environment using the serverless Cloud Composer approach. The version 2 environment enables worker auto-scaling and runs on top of the robust Google Kubernetes Engine Autopilot system. The Autopilot approach gives us the benefits of Kubernetes open source control and visibility, all in a fully managed environment where we can control, think about, and pay for pods instead of worrying about nodes. Next, give your environment a name and follow the instructions to set up the IAM role. Now, let's make a choice on how to set up our environment resources. Remember, if you're just experimenting, shut down your environment when you're done to save costs. The smallest environment is still over $10 a day, so if you're looking for a more budget-friendly option long-term, consider going with a custom resource specification approach. Finally, the default networking configuration, maintenance windows, and snapshot setup should be fine. Now, let's hit Create and launch our Cloud Composer environment. While our environment is being created, let's prepare some of the required code. We'll be using Google Cloud Shell IDE. But don't worry, as long as you can authenticate with Google Cloud, you're free to use any IDE environment you prefer. Together, we'll kick off a new repository for our code and call it Media Processing Airflow. Our mission? To create a DAG specifically focused on the use case of transcribing an MP4 file and saving that result to cloud storage for potential use in downstream systems. This may be a simple example, but it'll showcase the concepts we introduced earlier and can be easily adapted to other interesting media processing use cases. Now, let's capture the definition of our DAG, provide default arguments for the DAG, and handle required imports. With the scaffolding now in place, brace yourselves for a step-by-step DAG creation. Our first challenge will be using ffmpeg to convert our MP4 video file to a WAV audio file. We'll harness the power of the Kubernetes Pod Operator to accomplish this task. This grants us incredible flexibility over the libraries we use in these steps, as we're nearly at the infrastructure level of control and specification. We'll specify a Docker image here, which you're welcome to use. However, in a steady state or production environment, we recommend using your own image. Even in that case, you're not alone. We'll share some Dockerfile code to help you out. In this Docker file, we're merely installing the ffmpeg library and the Google Cloud SDK and running them in a more production-savvy way with a teeny entry point. We also need to create an entry point bash file, allowing us to execute various ffmpeg-based file transformations. What's our secret weapon here? We'll consistently use Google Cloud Storage to simplify both input and output handling, and we'll enable a wide variety of ffmpeg commands using transformations specified as an environment variable. It is essential to strike a balance between generalization and security. While making this solution adaptable to various situations can be tempting, it can also create challenges in maintaining security. If you don't have strong controls around your Composer environment or have a particularly security-sensitive application, consider avoiding the eval function and instead use a more prescriptive, controlled ffmpeg workflow. In any case, we've successfully created a container that performs ffmpeg transformations and is backed by Google Cloud Storage. Next, let's specify a bucket and file path for our video and determine where to save the WAV file, the extracted audio, in the same bucket. Our transformations will remove the video, use a specific audio codec for the WAV file, apply a 48K sampling rate, and handle the stereo audio with 2 channels. Now, let's import the necessary components and define our file paths by adding constants for the GCS bucket and file paths at the top. Next, we need to parameterize the file paths for the MP4 and WAV files, adding flexibility to our DAG. Although we're hard-coding the GCS bucket, you could easily turn this into a DAG run configurable property to accommodate multiple buckets. But wait, we haven't actually created the bucket yet. Let's do that together while our media processing environment is being created. A multi-region approach should work perfectly, and we'll choose Auto class, which automatically moves objects between different storage classes for cost and performance optimization. For simplicity, we'll go with Uniform Access Control and keep our bucket private by enabling public asset access prevention. No need for versioning or any other fancy features. Let's go ahead and create the bucket. Back to our code, it's time to acknowledge one big issue. We can't actually use the Google Cloud speech-to-text operator. Why? It only supports short audio transcription jobs at the moment. But fear not, we'll create a custom operator together to handle long audio transcription jobs. This will also serve as an excellent example of extending operators. We'll define our custom operator as a subclass of the off-the-shelf one provided by the Google provider. In addition to the operator itself, we need to switch out the off-the-shelf hook for a different one, a long speech-to-text hook. This hook specifies a long-running recognize operation instead of a short one. Across both of the classes, we'll be very close to the open source code, making essentially just one single change, switching from recognize to long-running recognize. We also need to make the asynchronous recognize task synchronous, ensuring the Airflow task completes only once the transcription is done. We only need to redefine the methods and attributes that we want to change from the parent class. In this case, we're altering only the execute method in the operator and the recognize method within the hook. Now that our operator is defined, we can specify properties for the audio file extraction. We'll maintain the same details for the file, like the linear 16 format, 48,000K sampling rate, and stereo channels. We'll also specify the US English language and employ the video model, perfect for transcribing clean, production-like audio. Keep in mind that apart from the costs of running the Cloud Composer environment, we'll also incur expenses for using the speech-to-text API. For a couple of minutes of audio, it's usually less than a single US dollar. However, even if the costs are low, keep in mind the cost creep of connecting to many different services. Next up, we'll take the transcript from the previous task and clean it up, removing timestamps and other unnecessary information. To achieve this, we'll harness the power of a Python operator. First things first, let's define our Python operator near the top of the script. Since we have a JSON string from the output of our last step, we'll need to parse it using the loads method. This will give us a list of transcript lines, which we'll write into a temporary file. Voila! We now have a pure text file containing our transcript, free of timestamps and additional structure. For our final act, we'll upload a transcript file to Google Cloud Storage. To do this, we'll create an additional task using the local file system to GCS operator, a fantastic plug-and-play feature from the Google Cloud provider. This operator will take the temporary file from our last step and upload it to our bucket at a specified text destination path. So let's go ahead and create that text destination as another file in the configuration for the DAG runs. Let's put this all together and make this DAG flow come to life. In the DAG flow, we first extract the WAV file from the MP4. Next, we run a transcription task using the speech-to-text Google Cloud service. After that, we compile the transcript without additional encoding structures and timestamps, generating a shiny, new text transcript file. Finally, we'll execute the upload transcript task, bringing our action-packed DAG to a close. To operationalize this, there's one more crucial detail to tackle. Specifically, Kubernetes pod operators can be a little tricky, requiring lower-level access or permissions to run smoothly. To address this, we'll create an RBAC YAML file, which grants our composer system just the right amount of permissions to execute code within those pods. If you venture into Google Cloud's documentation for Kubernetes pod operators, you'll find the Composer User Workloads namespace. This namespace, created by default, has excellent access structures. However, we also need the default service account in the Composer namespace, which runs the Composer system, to be able to reach out to the Composer User Workloads namespace and perform tasks like creating pods and retrieving their logs. By adding these RBAC structures, we grant our Composer system more control over the underlying infrastructure. More broadly, the power of Kubernetes underpinning this Composer environment enables lots of flexibility and integrated architectures. Imagine the possibilities, tying your Composer system to other Google services with workload identity using config connector or applying policy-based controls for security. All of this is possible because it all runs on Kubernetes. Before we apply the RBAC, we need our environment to be ready. Let's do a quick check to see if our Composer environment has successfully provisioned. And it has. Fantastic. Now, let's head over to the Kubernetes Engine interface to see how this looks. We've spotted our Autopilot cluster and see the total CPU and memory requested by our Airflow system. Although Kubernetes powers this environment, it's entirely managed and serverless, so Kubernetes expertise is rarely required. With our terminal in hand, we'll obtain the cluster credentials and apply the RBAC file, setting up the necessary permission structures. Next, we'll dive into our Composer environment, opening the DAGs folder to drop in our Python DAG definition. In just a few minutes, Apache Airflow will recognize our new DAG and be ready to run. But wait, let's not forget to add an actual MP4 file for processing. We'll upload an example 4-minute MP4 file to the bucket. Thanks to our extended operator for speech-to-text, We can handle audio longer than a minute with ease. However, for much larger files, keep in mind that you may need to increase CPU, memory, or ephemeral storage allocations in the Kubernetes Pod Operator definition. Back in Apache Airflow, we eagerly wait for the DAG to appear. If you encounter any Python syntax issues, Airflow will alert you with a helpful error message. For added convenience, Google Cloud offers additional information tabs and the ability to install necessary Python packages through the PyPy Packages tab. With anticipation, we trigger the DAG inputting simple file paths with the same file name and different extensions. As we monitor the DAG's progress and examine the logs, we stumble upon a minor issue in our setup: an incorrect namespace in our RBAC settings. With a swift fix, we're back on track to witness a successful run of our DAG. If you're following along, use a Kubernetes namespace list command to get the correct value for your specific environment. The change in color indicates a retry in process, so we check if our permissions fix was successful. As the log unfolds, we see that the MP4 file was copied, ffmpeg ran smoothly, and the WAV file was uploaded back to Google Cloud Storage. With a triumphant return code of 0, this DAG run is off to a good start. As we move on to the transcribe task, we encounter an error. The API hasn't been enabled for our project. If we quickly enable it, we should be able to catch the fix on the subsequent retry. All right, things are looking promising as we see the waiting for operation to complete message, which means we've successfully triggered the transcription. We eagerly wait for the speech-to-text service to finish its task. Not too long after, we see that the end-to-end flow was a success.
Hooray! Yay!
Now we can examine the end result of this pipeline in our cloud bucket. As expected, we find the example.txt file containing the transcript. Upon downloading and viewing it in our IDE, we can see the raw transcript structure from the service. This foundation for media processing using Cloud Composer can be extended and customized in numerous ways. We hope we've showcased enough key components to give you the confidence to tackle the next steps and adapt this to your specific use case. We'll be keeping an eye on the comment section for any questions and want to thank you for tuning in.